Welcome to today's Explainer. We all use databases literally every single day, mostly without a second thought. But right beneath that slick app interface you're tapping on is this absolute mechanical marvel of data organization. Today, we are popping the hood. We're going to see exactly how these systems manage to store and retrieve massive amounts of data with lightning-fast speed.
So, I want to kick things off by throwing a massive, kind of counterintuitive paradox your way. Take a look at the question on the screen. What if I told you that the absolute fastest way to update a piece of data on a hard drive is to never actually overwrite or delete the old data? I mean, it sounds completely backwards, right? In our physical world, if you want to update a whiteboard, you erase the old words and write new ones in their place. But in the high-stakes realm of databases, updating in place, that can actually be a massive bottleneck.
Which brings us to Section 1, the append-only paradox. To get why this paradox is actually the secret sauce for crazy database speed, we have to look at something called the append-only log. It is exactly what it sounds like, a sequential data file where new records are strictly added to the very end. Old data is never overwritten. It's never erased in place. Think of it literally like a receipt printer at a grocery store. When a new item is scanned, the printer doesn't magically scroll back up to erase a line, it just prints a brand new line right at the bottom of the roll. If a price updates, you just print a new line at the very end saying, "Hey, new price." It is, without a doubt, the simplest, fastest possible write operation you can perform.
Okay, let's dive into this a bit deeper. While appending to a log is incredibly fast for writing data, it creates a massive nightmare if you actually want to read that data back. Think about it. If you have millions of records in a flat file, and you need to find one specific key, you literally have to start at the beginning and read every single line until you hit it. In computer science, we call this an O of N cost, and it means terrible performance that just gets worse and worse the more data you have. So, the solution? We use an index, specifically an O of 1 hash index. This gives us blazing fast lookups no matter how huge our data gets. The index acts like a giant signpost living right alongside your data, telling the system exactly where to look.
Let's see how this works in Section 2. Enter the hash index. We're going to look at this through the lens of Bitcask, which is the default storage engine for the React database. And what's really interesting about this slide is just how remarkably simple the structure is. Bitcask keeps an in-memory dictionary, a hash map. Look at the first column, you've got your keys. Let's say they're IDs for cat videos, right? Kitty 00000. Then in the second column, you have the exact byte offset on the disk. This hash map acts exactly like a treasure map. Whenever you append a new key-value pair to the end of your log file on the hard drive, the system immediately updates this in-memory map to point to the exact spot where that new data just landed.
This sets up a beautifully mechanical, four-step journey whenever a read request comes in. Step 1, the database checks its blazing fast RAM for the requested key. Step 2, boom, it instantly finds the byte offset. Step 3, it tells the hard drive to jump to that one exact specific spot in the file. And step 4, it reads a value. That's it, just one single disk seek. And honestly, if the data's already hanging out in the file system cache, it doesn't even need to touch the physical disk at all.
But there's a catch, which brings us to Section 3, the compaction solution.
So, the elephant in the room. We have a looming conflict here. If we only ever append to the end of the file, and we're tracking every single tiny update, won't this runaway train of data completely fill up our hard drive? Well, yeah, it totally would. To escape this, the database uses a brilliant trick called compaction. First, instead of writing to one giant, infinite file, it breaks the log down into smaller segment files. When a segment hits a certain size, it closes it up and starts a fresh one. Then, running quietly in a background thread, so it never interrupts your active reads and writes, it goes through and throws away all the duplicate, outdated keys, keeping only the absolute most recent update. Finally, it merges these cleaned-up records into a brand new, much smaller segment file. Once that's done, the old, bloated files are safely deleted.
There's this great quote from Martin Kleppmann in our source material that says, "Appending and segment merging are sequential write operations, which are generally much faster than random writes." This one sentence is basically the ultimate teaser for the climax of our explainer. The whole reason we go through all this trouble with segmenting and merging and compacting, it is all about one thing: raw, unadulterated speed.
Let's break that down in Section 4, the need for speed.
This is where it all comes together. We have to look at the literal physics of data storage to understand why developers are so eager to use append-only logs despite needing that whole complex background compaction routine. It all boils down to the stark contrast you're seeing here. Sequential writes are unbelievably fast. Whether you're on an old-school spinning magnetic hard drive or a super-modern SSD, writing data in one continuous straight stream requires almost zero mechanical movement or overhead. But random writes, the ones that happen when you try to update a file in place, those are painfully slow. The disk head has to physically jump all over the place to find the right block, or the SSD firmware has to do all this heavy lifting. By just appending to the end of a file, we completely bypass that random write penalty.
And this brilliantly illustrates why the append-only design is such a massive winner. It's not just about raw write speed. It literally makes everything else easier too. Take concurrency control. It's way simpler because those old segment files are immutable. They never ever change, so multiple threads can read them at the exact same time without locking up the whole system. And crash recovery, it's a breeze. You never have to worry about the power failing right in the middle of overwriting a value, leaving you with some corrupted, half-old, half-new Frankenstein data. Plus, that background merging process we talked about actively prevents your files from getting fragmented over time. It is a seriously elegant system.
But we have to talk about Section 5, the fatal flaws.
Because in the world of software architecture, every superhero has its kryptonite, right? There are literally no perfect solutions, only trade-offs. And Bitcask is definitely no exception. So the absolutely crucial point here is this number on your screen, 100%. For this entire beautifully fast architecture to actually work, absolutely 100% of your distinct keys must fit into your server's available RAM. Period. If you have a workload with a massive number of unique keys that outgrows your memory capacity, this storage engine will just fundamentally stop working for you.
Now you might be thinking, okay, well if I run out of RAM, why not just move the hash map onto the hard drive? It's a totally logical thought. Actually, scratch that, it sounds like a great fix, but moving the hash map to the disk simply doesn't work in practice. Maintaining a hash map on a physical disk requires a massive amount of expensive random access I/O, which completely destroys the entire point of our fast sequential writes. Plus, trying to manage hash collisions on a disk is notoriously fiddly and slow. You really, truly have to keep that map in memory.
So, summarizing Bitcask's kryptonite, we're left with two really severe trade-offs. First, RAM strictly limits your keys. This engine is absolutely perfect if you have a moderate number of keys that you update millions of times, like, say, view counters, but it's terrible if you have billions of unique, single-use keys. Second, range queries are just awful here. Because a hash map scrambles the order of your keys in memory, you can't just easily say, hey, give me all the keys between kitty 0000 and kitty 9999. You would literally have to look up every single possible key in that range individually, which is completely unworkable.
Which leaves us with a final, pretty provocative thought to wrap up on. We've seen how ignoring the intuitive idea of updating in place and totally embracing the append-only log unlocks some seriously incredible speed and reliability. But it demands a strict toll. Your keys have to live in memory. So the next time you look at the data structures powering the apps you use every day, ask yourself, in the race for database speed, are your keys small enough to pay the toll? Thank you so much for hanging out with me for this explainer. Keep learning, keep questioning, and I'll catch you next time.